So just to give me a few organize those notes. So today I will just briefly recall the Markov property, and then we go on to the next section on recurrence and transient or Markov chains. So I will just write on the iPad. Okay, so let's start sharing screen. Okay, so let's just start. So last time we mentioned, and I told you the proof just briefly in the end about the strong Markov property. So let's just briefly recall strong Markov property because we will use this. Okay, the strong Markov property. So because so what was the strong Markov property? So it says the following. So we consider a sequence of random variable or just a bounded variable function. Suppose for each n, so we have a bounded and a variable function. So this is bounded and variable. So omega 0 here, right, is just our the sequence space, right? The S to N, right? S is the state space, the state space, Okay. So Yn is a sequence of bounded functions defined on omega 0. And also we wanted bounded, right? Let's just write like this. So then, and also we have a stopping time, and n is a stopping time. So n is a stopping time. So it can be, so we don't need this assumption, right? So you can think n is almost surely finite, but this is not essential because so our conclusion is on the set, the stopping time is finite. So then we have the following, right? So this is expectation. So mu is the initial measure, initial distribution. So theta n is a shift, is a random shift. Right? So Fn is the information generated by stopping time n. So this is strong Markov property because now the shift depends on stopping time n. Okay, so this is the equivalent. This is equality for two random variables. Okay, and these are only true, right? These are true on those set. Right? On the set, the stopping time is finite. So I want to emphasize So where so where so where so the right hand side so means this, right? First we take a function fxn so equals to e, take expectation, right? Starting from initial Dirac x yn, right? So then so e x n y n it means phi x n. Okay, then we evaluate x as a random variable xn, and n is just stopping time. Okay, so this is a strong Markov property. This is strong Markov property. This shows the independence, right? Can be trajectory wise, right? It doesn't so if you compose with stopping time, the independence property also true. Right? So this is a strong Markov property. So I will just skip the proof because the proof is basically just so the proof is done by breaking and conquer, right? Breaking and conquer. Break and conquer, right? Break and conquer. Is done by break and conquer technique. So we just break the all possible values of the stopping time n, right? So n can be 0, 1 to n, right? To infinity. And we just write using the definition of conditional expectation. So, but now let's talk about a few application, but not actually just start what our discussion on transient and recurrence. So I will just start on our discussion on recurrence and transient. Transience is okay. Okay, we just start that. The first result we show, right, is just a direct corollary of the Markov property I showed you, right? I just showed you, right? It's just here. It's just this, right? Markov property right here. So how to do this, right? So let's set several settings, right? Let's define. If you have questions, just let me know, right? It's and sometimes the internet is unstable. So I have some meetings yesterday, and it stops twice, but it never happens during the lecture time. So maybe this is the time. Most people have lunch. Okay, so it's not stable, right? You can ask any questions. So so first, let's define a sequence of stopping time. There's dy0. Dy0 is just a 0, right? It's a convention. And we define, so for k bigger than 1, we define a sequence of stopping time, tyk. So tyk is the increment of all the integer which is bigger than tyk minus 1, such that xn equals to 1. Okay. So what does this mean, right? So this just means, right, the case return to 0. So this means the time. So this means the time of case return to y. And since ty is 0, right? So you can check, right? You can check. So ty1, right? Since ty1 equals to infinite, right? According to the definition, star here. So ty1 actually is just n bigger than 0, right? x equals to y. So this is the first return to 0 to y. And so since ty0 equals to 0, right? Since ty0 equals to 0, so any time, so any visit and time 0. So even x0 equals to y, right? So any visit and time 0 does not count. Does not count. So this is slightly different, right? So and this is just to emphasize. Sometimes you read the proof and something this is important. It's called the 0 time does not count. Does not count. But otherwise, it's all the same definition we used before as like n's return to real, n's return to y to a fixed point. Okay, so then by the strong Markov property, so we can show we have the following property. We have the following theory. So the following theory says says this, right? If we're starting from x, and we want to compute, right? So the case return to y in finite time. So this is a probability, right? You're starting from x and you return to y case time and infinite time. Case infinite time, right? The infinite time. So this equals to rho xy and rho yy k minus 1. I haven't defined this. So rho xy. So rho xy actually equals to, right? If you're starting from x and ty is just, so ty is just ty1, right? Let's write here, ty1. And rho xy means you start from x and you return and you reach, you arrive y infinite time, So similarly, right, rho yy, right, just you're starting from y and you arrive y infinite time, right? So this theory, right? So this equation actually is intuitively very easy, right? So intuitively, it's almost trivial. So why I said so? Right? Because so what does this mean, right? So let me use another color. For instance, here, right? So let's say if you're starting from, this is not very easy to see. So let's say if you're starting from x, right? Initially starting from x, and so in the end you return to y, so k times, right? So what can you do, right? So first you just arrive, you just to visit y for the first time. For the first time, right? So for the first time, you can compute all the probability, right? So first visit y, right? You can visit y like this, okay? So then when you first visit y, you just keep visiting y for k minus 1 times, right? K minus 1 times. Since this is a Markov process, Markov chain, right? So once you reach y, right, it really doesn't matter of your history. So that's why you can just multiply those two probability to probability together, right? So this is not two, actually, this is proved by action. But anyway, so this is using a strong Markov property. I will give you the proof. You can read the proof in the textbook, but let me just give you a quick proof. This tells you like how to write, how to make the intuitive idea rigorous. Right? This is just one example, right? Let's prove this. Okay, so let's prove this. So if you can open, right, so somehow, right, if you can just open the textbook, right, then might be good, right, because sometimes you cannot see theory, right, when I do the proof. So you can just open the textbook, right, for reference. So how to do the proof? So first, so if k just equals to 1, right, is of course this is proved by induction. If k equals to 1, right, it's very trivial, right? So the left-hand side is just ty1 less than infinity, right? ty1 is just a ty. So we should just rule, right? So this is trivial. This is trivial. So then so we suppose k is bigger than 2. And so we give you an example, right, like how to define an indicator function, y, right? How to define a y? So let's define a y. So this is what we used, right, in the strong in the statement of strong Markov property or in the Markov property. So this is kind of indicator function. So which tells you, right, which events you are interested. So for some n bigger than 1, and 0 otherwise. So what does y tells you, right? Y is kind of an indicator function. So y, y omega, right, equals to 1, right? So if, right, if the path, right, if the path visits 0, visits y sometime, right, and positive time. So as I said before, right, so this proof, 0 time really doesn't matter, right? And 0 initial doesn't. So now let's define, because we are using induction, we just want to split things. So we choose stopping time. This is really a stopping time. So ty k minus 1. So then, so you can check, So if we shift the amount of n, right? If we shift the amount of n, and if this equals to 0, that means, right, tyk is less than infinite. So why, right? So why, right? Just to give you an example, right? Let's say this is let's say this is the time, right? This is 0 time. So this is just a time, okay? Let's say, oh, so bad. Okay, so let's label. Let's just label. Let's just label the time which we tend to right. So this is a ty. This is ty1. So this is ty2. Right. Okay. So this is ty k1. Right. This is ty k. Okay. So so now we know, right? So n is ty k minus 1, right? So here so here is 0 is 0. So when you do this shift, right? When you do this shift, right? When you do this shift, what do you get, right? So originally, right? So this is the first one, right? So when you do the shift of the amount n, right? So you shift to the left. So this number, this becomes 0, right? This is becomes a 0 coordinate, right? This becomes a 0 coordinate. So if tyk, so if tyk is less than infinite, right? So I mean, I told you, right? So 0 doesn't matter, right? So if tyk is less than infinite, right? So that means, so for those new sequence, right? For this new sequence, it visit y and a positive time and a finite time, right? So this is true. This is true. And this is not just if, right? It's if and only if and only if. Okay. So now we just use strong Markov property. So by property, by the strong, I will just shorthand, right? Just using strong Markov property. So we have, right, starting from x, y, we do some shift, we do shift, and condition on the information generating by the stopping time n is equal to, so now, right, so we just starting from xn, and for y. And this is true on n is less than infinite. Okay. So it's just a strong property. And we know, right? We know. So since, so we know, so on n less than infinity, you are on less than infinity. So actually it's n. So what is xn, right? So what is xn, right? This is n, this is n. And so this is the time visit 0. So of course, right, xn equals to y, right? The definition of the stopping time. So, so the right hand side here, so here, right? So here is just given by, so now there's no randomness, right? So it's just a y for y, right? So what does this mean, right? What does this mean, right? So this means, right, so by the definition of y, this just means you're starting from y and you return to y positive time, right? And by our shorthand, right, so this is just rho y, okay? So let's just write like this, okay? Okay. So also, right, so let's just the proof, right? Also, we have this. So px, so this is the left hand side, right? This is the left hand side. So what does this means, right? So this means you integrate, I will explain it slightly later, x, y. So what does this means, right? Why this is true, right? Why this is true? Why this is true? Why the first equality is true? So this equals to, right, ex, right, ex, and you integrate the test the indicator function, right? So is it, so the probability is just to integrate the probability the function, and so which is, so which actually is just this, which actually just this. Right? So why, right? So because here, right, so K is finite, right? TYK is finite. What does this TYK finite means what, right? You just look at this, right? If this is finite, right? So first, n must be finite, right? The stopping time, this must be finite, right? Because this is bigger than this, right? So if this is finite, right? This is should be finite. First, this is finite. Then you have one more visit, right? So that's why you do the shift, right? You do the shift, and you also get finite, right? You also get finite. So that's why you ends up with the set y. Right? So these two are just equal. Right? Are just equal. Okay. So the next is just we use the from here we use the definition of conditional prop expectation. So this is the euro, right? This is the euro. This is the euro expectation, right? Just to integrate on this set, on this set, on this set. So now we write the expectation, right, of the conditional expectation. So then we can use the Markov property. So this is the property of conditional expectation. So now we can use the now we can use the Markov property right here, right? We just use this property, and this give you rho y, right? So we have is just ex, right? Rho y is constant, rho y constant. You integrate a constant on this set, right? So what we get is rho y, and so ex n less than infinity. So which is exactly rho y. So we're starting from x ty k minus 1 less than infinity. So then we just then by induction. So we can conclude. So by induction. Okay. So then that's it. Okay, it's not a very hard proof, right? Intuitively, it's very easier, but so this give you example like how to using the strong Markov property, how to using the strong Markov. So in the textbook, there's one more example. So I won't talk about that because I already write a lot of notes. Example is called the reflection principle again. Reflection principle. I definitely suggest you read that. Right? It's very hard to read. But when we're talking about Brownian motion, we will go back to this again because this is used in Brownian motions as well. So what is the basic idea, right? Basic idea is the following, right? So if we have a random walk, right? Simple, not a simple random walk, it's a symmetric random walk. If we have symmetric random walk, so which means we have Sn, right? Let's say on R. So Sn equals to cosine 1, cosine 2, cosine n. So S0 equals 0. And cosine I are IID. So all cosine I is symmetric, has a density function or probability distribution, which is symmetric with respect to 0. So basically it says, right, so I mean symmetric on 0, you know, right? So you write the distribution function is symmetric with respect to 0. So x and minus x has the same mass, right? So basically, right, cosine I equals to x, cosine I equals to minus x. Basically means the following. So the conclusion, right? The conclusion is like a very nice conclusion. So in case, this is a very useful observation, right? So this is a statement for a bigger than 0. So then, so the probability of supreme m less than n Sm, so big than A is less than 2 probability Sn bigger than so here, right? So here, right? You can put to be this. You can put to be strictly positive, right? This really doesn't matter, right? Doesn't matter. So the idea, right, is the main statement, right? The main statement of the theory of the reflection principle here is like, okay, so the probability of the maximal one, right? The maximal value is bigger than A, right? Can be controlled just by the endpoint, right? So if you know the probability of the endpoint, right, you can just compute the probability of the give a bound, right, or the probability of the the maximal value. So this is the control of the maximal value, right? This is just the control of one endpoint, right? So of course, this is more easy to compute, right? So this is much easier to compute. This is much easier to do. Right. So we also have, for Brownian motion, we also have the similar version of this reflection principle. And for Brownian motion, right, so this is given by a Gaussian distribution. So you can compute the Gaussian, you can compute this value, right, just by input, right, by Gaussian, because we have the density function for Gaussian then or estimate them. So we can compute this side. You can read the proof, but I want to skip that. So before I go to next section, so I just spend 2 minutes talking about another, just to mention this result, right? This is a statement in the edition false, in false edition of the textbook. Now it is exercise 2.2. So this kind called probability or properties of infinite opportunities. It's kind called of infinite opportunities. So what does this says, right? This is your exercise, your homework problem. So it says, right, if X is a Markov chain, and we have this condition, so probability of m equals to m plus 1 to infinite. So x m in Bm, so condition xn is positive on all the set xn in an. So then, so this is assumption. So then the probability xn in an infinite open minus xn in Bn infinite open equals to 0. This looks like a very weird story, right? So there's a hint, right? Hint you using Levy 0-1 law. But let me just give you a little bit hint, right, of this. So basically, you kind of need to show, right, the set, this set, contain in this set. So like this set is kind of bigger. So you can use the, so you can use the conditional, the Lebesgue dominated convergence theory for conditional expectation. Okay, that's an intuitive explanation of this theory. So this theory is by someone like if you so this for this means right, you cross a street, right, you cross a street. So each time you cross the street, right, you have positive chance to be get hit by a car. So this means right, you cannot cross, right, this is like you cannot cross the street infinite often. So because so it can be end with hit by the car. Uh, yeah. So yeah. So there's an implication, right? There's an implication of this theory. The next result, you can check that this is a homework problem. Yeah. So you don't use Levy's 01 law. You can just use Lebesgue dominated convergence theory for conditional expectation. I just end here and start the next section on recurrence. Okay. Okay, so let's just recall, right? We use all the notations before, and ty0 right equals to y8 equals ty1 equals to ty, right? So which is defined as the infimum of n, which is bigger than 0, right? So xn equals to y, right? It's the first return to y, and also we can define tyk, right, inductively. Also, we define the rho xy. So rho xy is the probability you starting from x and you end with y infinite time. So this basically what does this mean, right? So what does this mean? Yeah, what does this mean? Right? So this means starting from x, right? What is the probability you reach y in finite time? So if x, y than 0, if rho x and y is bigger than 0, means there exists paths, right? There exists a path connecting state x and y, states x and y. Okay. Yeah. So I mean, if I give you an example, right? It's much easier to see. Let's say we have a state 1, right? We have a state 2, right? We have a state 3, right? Let's say this is 0, 8, right? So 0, this is 0, 5, right? There's 0, 5, right? So let's say 1, right? 1. So of course, right? So I mean, you can put row 9, right? So this is not really important, right? So here, right, you can check, right? You can check very easily, right? Actually, row 3, row 3, row 3, 1, right? Positive. Row 3, 1 is positive, of course, right? So why row 3, 1 is positive, right? Because there exists a path right here, right? Here, right? To reach 1, right? To reach 1 from 3, to reach 1 from 3, right? So uh, but you cannot reach 3 from 1, right? But you cannot reach 3 from 1, right? So because why, right? So from one you can reach 2, right? From 1 you can reach 2, but you can from 2 you can really not reach 3, right? So actually this is a block. This is a block. Later we can show is recurrent, and this is a transient. This is transient, and these are recurrent. These are recurrent. These are recurrent. Okay. So let's just define what is recurrent. We see this before we when we study a little bit about random walk. So why in the state space? So let's just fix all our discussion on those variable space. Variable space. So let's fix all our discussion on the variables. And so y is state. So y is called recurrent. So it's called recurrent if from y. So you always ends with y infinite time. So intuitively, what does this mean, right? So intuitive explanation is important, right? So it means, right, every possible way. So I need to find the exact way, right? I saw a very good explanation. So just give me one second. I find a very nice to explain that. Okay. So what does this mean, right? Intuitive. Right? So intuitively it means, right? So let's just copy some explanation, right, from online course by Jones, by the professor. So the course who took the course I just sent to you honestly. So I mean, it's mathematically, right? So it just means this, right? So if you just do a concrete example, right? So some intuitive picture, right? That's helpful. What does this mean, right? So this means starting from y. So if we're starting from y, so from whenever you can, from whenever, wherever you can go, there's always a way of returning to one. So this is called recurrent. Right? This is called recurrent, and the opposite side of recurrent is called transient. Right. So if you know current, right, the opposite side is just transient. Okay. So from the definition, right, we can very easy to check here. So the state 3 is not is transient, right? It's not recurrent. Why this state is not? Why this state is not recurrent, right? It's transient because, right? So here, right, you have 9 point. You have 0.9 probability to go to 2, right? And you never return, right? Right. So you never return. You never return. You never go back, right? So it's an intuitive explanation, right? But we need to prove theories, right? So we need write some several corollaries, right? So let's just write several. Okay. So if y is recurrent, right, means rho y equals 1, right? So this by the previous result. So what I get by the result, right, is this result. Is this result, right? By this result, right? From x you reach y. From x you reach y in k steps, right? In k times. Right? Not k step. So equivalent to you first reach y and and you then you visit a y, right, for k minus 1 times, right? So if this is 1, right, if this is 1, right, we can also get, right, if this is y, right, py, ty, k is also 1, right? So this is 1, this is 1, we always get 1. Okay, so then, so what we can get, right? So we can get it from y, ty, k less than infinite equals to 1. So this is true for any k equals to 1, 2, 3, etc. Right. So a direct corollary, right? So x and y. So if y is recurrent, then you start from y. So you visit y infinite often. So this event actually has full measure. Has full measure. You can easily check this. It's not very hard to prove. Okay. So what this means, right? So if we write n, so if we write ny, so ny is the number of times it visits the Markov chain visit y, right? So this is the number of the Markov visit y, right? Of course, right? So this is infinite, almost surely, right? So one y is recurrent, right? So if you take expectation, right, going from y, right? This means the we starting from y, right? So this equals to infinite. So if you have questions, let me know, right? So I think it's easy, actually. But if you have questions, you can let me know. Okay. Okay, so otherwise, right? So let's say y is transient. So y is transient. So y is transient. So what is? Let's compute this. If y is transient, let's compute. We're starting from x, and we compute the expectation of the number of visit to y. Right? So this is the number visits to y. Right. So this is just e to x. Take indicator n equals to y. Right. Is this account how many times, right, the Markov chain visited y, right? Okay, so what's that, right? What's that? Okay, so if you and just compute the dictation, right? So how to compute that, right? So you can take these two. So it's just a different way to write the integral. So it's just a different way to write integral, right? For this is integer value. For integer value, we can always write like this. Yeah. So you can check that, right? So the way is to write like, okay, right? So here's k, so b and y equals to k, right? So then we sum up with k, right? But if you change this, right, to be the sub level, right? So then you don't need to write this, right? So we use this several times. So now this can be written as k equals to 1 to infinite. So px tyk less than infinite, right? So the number visited y bigger than k time means, right, means this, right? Just means this. Okay. So from this theory, right? So we theory just prove we have px, right? So first we from x to y, right? Then from y to y, k minus 1 time, right? So we can take out rho xy and do the sum. So which is just rho xy. minus rho yy. This is finite. Since y is transient, right? So rho yy is less than 1, right? So that's why we that's why we get this, right? That's why we get this. Okay, so if we sum up the two cases, right? So we get the characterization. So it's 5.31. So y is recurrent. So y is recurrent as long as y equals to infinite. Very easy characterization. It's a very easy characterization. So I want to change one color, right? Let's change a color. Maybe this. Okay. So this is a very easy theory, right? So I want to prove another theory. So to show this, right? Let's just give you maybe just let's see one example, right? To see, so this example. Yeah, maybe I just cook up an example. Okay, so just use the previous example, but I want to write it here again. Right. So let's say we have one, we have two, we have three. So let's say, so here, right, there's 1 to 1 is 5.3, right? From here is point 0.3, right? Here is 0.2, okay? Let's say, so here it reached to 3, right? Here it 7, but 3 right here is 0.7. So just example, right? I just want to give you an example. Okay. So this is a Markov chain, right? Definitely this is a Markov chain. So you can see, right? This, so this is actually a transient, right? This is a transient. And why this is transient, as I said, so there's some loss or mass, right? So this type of, you can think this, you can think there are many mass, right? Ensembles, right? Many mass on, right? So if you do each iteration, right? So you don't really need to care about the self transition, right? So when you do one iteration, right, there's this amount of mass, right, percentage of mass, right, there's 30% of mass goes to state 2, the 20% goes to state, right. So in the end, right, so there's no mass, right, there's no mass in 1, right. But these two, right, so distribute mass between 2 and 3, right, and you can really check this is recurrent, right, this is recurrent. This is recurrent. Yeah, you can check just using definition or something, some other things. Following theory, we have let me show you another theory. In this theory, we can distinguish, we can find recurrent or transient state. Okay, so this theory is very useful, right? Basically, like basically just make it rigorous the previous argument or intuitive argument. Okay, so it's following, right? We have a state X, right? If X is recurrent, let's see, if X is recurrent, and rho X, Y, right, is bigger than 0, so then Y is recurrent. And this is not done yet, right? And rho y x equals to 1. So what does this says, right? What does this says, right? This says, okay, first, let's say x, right? You have a state x, and we have a state y. So if we a priori we know, right, x is a recurrent, and we know, right, x can reach, right? So there's a certain path, right? There's a certain path from x, and you can reach y. So this rho is bigger than 0, right? So then we can show it's also different. And not done yet, right? So then, and also rho y x equals to 1. So that means from y, you can always reach y. From y, you can always reach x infinite time, right? So of course, right, since this is true, right, this is true right now, right, from this, also prove, right, rho y equals to 1, right? Okay. So this is called contagious. This is called contagious. This is called recurrence. Recurrence is contagious, right? So if this state is recurrent and y is reachable from x, right? So then y is recurrent as well. Okay. Yeah. Okay. Let's just do the proof, a very short proof, just to give you the idea. So I will do this proof, right? Because this is one of the basic proof. Then I can skip out all your reading. Okay, so first, let's show let's so rho y x actually equal to 1. I will yeah, maybe I just do the rigorous proof. Okay. So let's just show this. Okay, let us show this by contradiction. So how to show that, right? So let's assume. So this is what we want to argue. Assume, so if rho x is less than 1, right? And we already know, right, rho x is bigger than, right? So if this is true, right, so then rho xx is less than 1. Rho xx and less than 1. Right, so this is actually very easy to believe, right? Intuitive idea is easy to believe, right? So what does this mean, right? So let's say, so this is state x, this is state x. So x, from x, you can always reach, y, right? So this is infinite time. So you have task to reach y. But anyway, so this positive part, positive mirror. So as I said, right? If x is recurrent, right? If x, so that means all the mass you send out, also including those mass you send out to y, you should come back, right? You should come back. So, but so if so then so let's consider, right? So then, so what does this means, right? Rho yx is less than 1. Rho yx less than 1 means this, right? That passes, right? You can going from y to x, right? But since this is less than 1, right? So there are certain possibilities, right? You're starting from 1, this y minus xy, and this is, right? So there are possibilities. So there are some mass cannot go back to x, right? So this is the idea. So since rho yx is less than 1, right? So as long as you reach x, as long as you reach y, right, you cannot come back. So this is true. Then this is true. This is idea, right? This is idea. We make this just using several lines to make this rigorous. Okay. So let's choose the so since let us choose k is an integer. Let's choose the integer, which is the infimum of the small number k, such that this is bigger than 0. Okay, so let's say so pxy here is just the conditional. So xn equals to xk equals to xk equals to y, x0 equals to x. So it's like you the k step, right? So here is x. You coming from k steps and you ends with y. So this is the probability. So k is the time or steps. Okay. So k is the system number such that p2k is bigger than 0. Okay. So then, so we have a path. So then there exists a sequence y1, y2, k minus 1, such that so px y1, p y1, y2, p yk minus 1, y, which is bigger than 0. So this is just you choose solid path connecting x and y, right? Since from x always reach y, right? So this is possible, and you definitely can the number small k such that you can move from x to y. Okay. So since now k is chosen to be the minimum, since k is chosen to be minimum, so all those yi is the x. So I equals to 1, 2, k minus 1. So this is not x. So otherwise you can shorten, otherwise you can make this k smaller, right? So this is y. So now we just write a formula to make those picture rigorous, right? So since rho y x, right, from y to x is less than 1, right? So from x, tx equals to infinite, right? You cannot so from x you cannot read to x. So this event, right, in particular contains the following. First, we move from x to y1, right? So then we move from y1 to y2, etc. We move from yk minus 1 to y. So then there is a certainty, right, from y. You cannot reach to x in finite time, right? So this is a probability. And this is bigger than 0, right? So this is not possible. This is not possible. So this false rho x is less than 1, right? So this is a contradiction. A contradiction. So hence our assumption is not true, right? So py from y, we can always reach x in finite time. Rho y x equals to 1, right? So we prove this. So then there are a few arguments, right, from rho y x equals to, so then we can prove, but I will skip the proof. We can prove that y is recurrent. Y is recurrent. How to show y is recurrent? You can just do this. You can just show this. What does this mean, right? So this means this is the probability of y written to y, written to y in n steps. The probability of y written to y in n steps. So you can really check, right? So this, what is this, right? This is ey ny, right? So then using the previous theory, we can the characterization, right? Using previous characterization. So you can use the previous characterization. Okay. So I will just skip that, right? It's very easy to do. Okay. Okay. So any questions? So let's change the color. Yeah. So let's just recall, right? Recall the theory, right? The theory, what the theory said, right? Theory said, right? If you x is recurrent, right, and you can reach y from the recurrent state, right? So then this state is also recurrent. Right? So for instance, right? For instance, if we know, right? If we know this 2 is recurrent, right? And we can 2 can reach 3, right? 2 can reach 3 in finite state, right? So this is a recurrent block. So this is a recurrent cluster, right? So we can, this is recurrent cluster. Okay. So let's so how to like do decomposition, right? How to distinguish all the recurrent state and transient state, right? So we need to show show the decomposition theory. So given you a Markov chain, we want to do the decomposition. So decomposition theory of Markov chain, right? So for instance, if I give you a Markov chain, how can you define all the transient state, right? All the Markov, all the recurrent state, right? So this theory, what does this theory says, right? So this theory says the following. Okay, so this theory 5.3.5 says the following. So let's choose all x. Let's choose again, right? We use as a space, right? Which the recurrent state, which the Markov chain is sitting on. So what is all the recurrent? Is all the recurrent state or recurrent states or recurrent states. So then we can decompose, or we can decompose this U, right? This U as a union. This is a union. So actually, this is a joint union. Since Ri has no intersection with Rj, right? This is joint union, and where Ri, so where I is closed and irreducible. I will just give you the definition of the meaning of closed and irreducible. Closed and irreducible. We probably didn't have a lot of time to cover the remaining part in the next lecture. So you probably need to read a little bit. Okay, so what is closed and irreducible means, right? So this theory, closed basically means closed basically means if you're starting from a point in the closed set, right, you are always there. So let's. So what closed means, right? Closed. And closed is not the notion in topology. Topology. So let's say what is C, right? Because C is closed. Of course, right? C is a set of the state space, right? So C is closed if we choose X from C. So, and rho xy positive. So then y is also in C, right? So the closed, this notion, right? So this is a notion, right, of a Markov chain, right? So of course, it is related to the structure of Markov chain, right? So the meaning is very simple, right? So first we have a state y, I have state y, and this is x and y, right? So if x is in C, and we know y is reachable, right? Y is reachable by from x, right? If this is positive, right? So then we can get y is also in C, right? So you can think in the following way. You can see in the following way. So if x is in C, right? C is closed. So then you're starting from x. If you're starting from x, then all the paths, so all the trajectory should be in C. Should be in C. So why? Why? So it's so let's say if you're starting from x, if you're starting from x, right? If you're starting from x, so the next step, right? What to move, right? So is here 0, right? Starting. So what is it, right? So if the next step is x1, right? So of course, right? Since this is positive, right? So this is positive. Otherwise, it cannot be there. So x1 is right. So then you move from 1 to, let's say, to from x2, right? I mean, so this is non-negative, right? So this is positive, but you cannot move there, right? So x2 should be in C, right? So this shows, right, all the paths contained in C, right? If the initial point is there, if the initial point is in C. So this is the closedness, right? It's the definition of closed, a closed set, right? There's another notion, right? It's also very important. Irreducible. It's called irreducible. It's called irreducible. It's called irreducible. So irreducibility, right? So what does this means, right? What does this means, right? Let's say D is is irreducible means the following. So if x, y are in D, so then x, y is bigger than 0. So what does this mean, right? So this means any point, right? Let's say this is D, so you have x and y. So any point in D, right, it can be connected, but not just from x to y, and also from y to x, right? So this means, right, any 2 points in D can be connected by path. Can be connected by path, right? This is irreducible. These two notions are very important notions, right? So all the discussion is focused on these two notions. So in particular, right, let's give you a very quick theory, right? We have 3 minutes or some that, but we can still state this theory. You probably need to read the remaining of this section and do like 2 problems. But not very difficult problem. Right? So theory. So this theory tells the following, right? So let's see is closed. So C is closed and finite. So finite, right, is easy to know, right? So it's easy to understand. It's just a finite number, right? So the cardinality of C is finite. So then C contains at least one recurrent state. So I mean, if C is closed and right, it contains at least one recurrent state. This is kind of, I mean, this is not exactly, but it looks like kind of like compactness, right? I mean, mass compactness, right, is not the usual compactness analysis, but it's kind of compactness, right? If it's closed and finite, right, it's kind of compact, right? You can have a recurrent state. Second, so if further C is reducible, so then all states, in C are recurrent. I mean, but this is trivial based on, so this is just by contagious property of recurrence, right? So why, right? Since C, right, let's say this is, right, it contains, the first part, it contains at least one recurrent point. And by irreducible, right, always reach Y from X, right? So X recurrent. And by irreducibility, right, show XY is bigger than 0, right? So we can get Y is also recurrent. Right, so this is part 2. Part 2 is trivial, right? Part 2 is trivial. And we need to show part 1. Proof of part 1 is enough. So we need part 1. But our time is there, but it's really short proof. You can read, yeah, maybe I just, if you have other things, you can leave the meeting. But I just spend 2 minutes on that. If you have a question, you can ask. So how to show this, right? So it's kind of a compact argument, right? But I mean, in spirit, but not really, right? Something like this, right? So we prove by contradiction. So prove by contradiction. We assume all y in the closed set is transient. So if we assume all those are transient, right? So this means, right, rho y is less than 1. And by the previous calculation, we know, right, starting from x, so let's just, right, so this x is also in C, right? Starting from x, so this is the number of visiting y, If you compute this, right, what we get is this. This is well defined. So we can this, right, because this is finite, and C is also finite. So we can sum up. So we can sum and also get a finite, we can also get a finite number, right? So this is finite. So to rewrite the integral, right? Let's rewrite the expectation. So that, as I told you, right? So this is a Pn xy. So this is just the expectation. Maybe that's not, I mean, we just first see this, maybe then not straightforward, but this is true. I told you this is true. You can think for a while why this is true. And since everything is positive, we can use in Fubini. So we just change the order. Just change the order. So what does this mean, right? What does this mean? So then what does this mean? So we choose X are in C, right? So Y is definitely in C, right? It's closed, right? So this, if you sum up with all Y, right? So this should get this 1. right? This is infinite, right? That's not right? Contradiction. Right. So this is not true, right? So this is wrong, right? So hence there exists at least one recurrent state. I will stop here, and if you have questions, I can answer. But otherwise, we can stop here. Yeah, we kind of slow, but that makes sense to many materials. So I suggest you to read all the remaining part. In particular, read MG1Q, MG1Q, and the generalization discussion. Yeah, so we don't have, so they have one homework problem related to this. Yeah, so I will just stop. If you have questions, let me know. Okay. What thanks? Does C is a finite mean? Does C is finite means C has, yeah, you're right. Yeah, C means it just have finite numbers of states, possible states. Yeah, I mean, you're still here, but this is recording, so I can still say that. So okay, definitely spend time to read the textbook, right? If you want more examples, you can have tons of online resources, and the lecture video I sent you last Sunday is very good, right? I definitely suggest to watch that and take some notes. Uh, but spend time going through all the materials in our textbook, right? But if you don't do now, right, probably you cannot catch up later. Yeah, but possibly I will do more lectures on this. So next time I will be quick. I will quickly go through this section, and I plan to talk two areas. Maybe Kromorov cycle theory, right? It's very useful when you do the MCMC, right? Monte Carlo Markov chain or Markov chain Monte Carlo, or some asymptotic behavior, but those are technical, right? So I'm not sure. Average, right? You talk two lectures and just skip the ergodic theory, then we have 3 weeks on Brownian motion. But if we talk too much in Markov chain, so there's no discussion on ergodic theory. Otherwise, we maybe spend one lecture on ergodic theory. Okay, so homework already posted is in the announcement. I didn't using the PDF file, right? So it's relatively easy, right, compared to other part, right? So okay, yeah, you can leave, but let me answer one question. Does C is finite means phi is finite? Since we said that there's a path from X to Y even. But it seems possible then to pass. Yeah, I will stop recording and